Good morning, everyone. I am Professor Rage Uday Kiran from University of Aizu. Welcome to my research presentation on the topic Discovering Closed Periodic Frequent Patterns in Very Large Temporal Databases. The outline of the presentation is as follows. First, I will be introducing you to periodic frequent pattern model and its limitations. Next, we will be discussing our model of closed periodic frequent pattern. Next, I will be talking about the mining algorithm, followed by experimental results, conclusions, and future work. Introduction. So periodic frequent pattern mining is an important model in data mining. It involves discovering all patterns that are occurring periodically in a temporal database. The classic application for periodic frequent pattern mining is monitoring traffic congestion in a transportation network. So I am just explaining an example here. So the picture that is to the left side is represents Kobe area in Japan. So the sensors that are located on the road segment generate us the raw sensor data at 5-minute interval. This raw data can be converted into a temporal database, and when fed to a frequent pattern mining algorithm, it discovers the sets of roads in which congestion was regularly observed in the data. For example, the pattern 145 says that the roads whose identifiers are 1, 4, and 5 are regularly observing congestion at 30-minute intervals. So when we have such kind of periodic frequent patterns, what we can do is we can interpolate rainfall data and other data sources for efficient monitoring of the traffic. Now coming to the problem of the model, the problem is the periodic frequent pattern model generates too many patterns, most of which are uninteresting to the user. For example, you can see that the user is only interested in 1, 4, 5 pattern, but the periodic frequent pattern model will generate all of its subsets, thus generating too many redundant patterns which are uninteresting to the user. Our objective is to prune those uninteresting patterns. So the contributions of this paper are as follows. We have proposed a new model of closed periodic frequent pattern. The advantage of our model is that closed periodic frequent patterns represent a concise, lossless subset that uniquely describe the complete set of periodic frequent patterns. So with very few patterns, we can still preserve the complete information of all periodic frequent patterns with our model. We have also proposed an efficient algorithm. Then by conducting experiments, we have shown that our algorithm is not only memory and runtime efficient, but also highly scalable. Then we have demonstrated the usefulness of our patterns with a case study. So now coming to our model, assume we have some set of items, okay, A to G. A subset of these items is called as a pattern or an item set. So for example, AB is a pattern. A transaction is a item set coming at a particular timestamp. So a temporal database is a collection of transactions. So you can see here at timestamp 1, the items A, B, C have appeared in the database. So this is how the temporal database looks like. Now let us collect the timestamps at which a pattern has appeared. Okay, TS of X. So now coming to TS of the timestamps containing AB. Okay, so A, B are occurring at timestamps 1, 3, 5, 7, and 9. Okay, so the support of AB in the entire database is 5 times. If the user specified minimum support is 4, then we say AB as a frequent pattern because the support of AB is no less than the user specified minimum support value. Once we define a pattern as a frequent pattern, now we have to look at the interestingness of this pattern in the time dimension. So now let's look at the dimension. Okay, so now we have some timestamps. Okay, we take 0, okay, which is the beginning and the end of the timestamps. Okay, so the AB has occurred at 1, 3, 5, 7, 9. So the dots represents the timestamps at which AB has appeared. Once we have it, what we do is we measure the periods or inter-arrival times. Okay, so we are measuring intervals. 3 minus 1 is 2, 5 minus 3 is 2, and so on. Then for correctness purpose, we measure two additional intervals from the beginning to the end of the database. Once we have these periods, what we do is we take the maximum period as the periodicity of AB, that is 2. If the user specified periodicity, maximum periodicity is 2, then we say AB as a periodic frequent pattern. So this is the definition of a periodic frequent pattern. Now coming to the closed periodic frequent pattern, we say as follows. Let X and Y be two patterns such that X is a subset of Y. Then we say Y is a closed periodic frequent pattern if support of Y equivalent to support of X and periodicity of Y is equivalent to periodicity of X. For example, in our database, the complete set of periodic frequent patterns and closed periodic frequent patterns are shown in table 2. Okay, you can see that A, B, which has support of 7 and periodicity of 2, is a periodic frequent pattern, but it is not a closed periodic frequent pattern because B's superset BC also has same support and same periodicity. So we do not mind B, instead we only generate BC. This BC still preserves the subset information of B in the database. So this is the advantage of closed periodic frequent pattern model. Now coming to the mining algorithm. So if we have n items, the lattice that gets generated is called the search space. For example, if I have 3 items P, Q, R, okay, the lattice of these 3 items represents the search space. Our mining algorithm performs depth first search on this item set lattice and discovers all closed periodic frequent patterns. In the interest of time, we are not explaining our algorithm in detail. Please refer to the paper. Now coming to the experimental results. For conducting experiments, we have used Dell server machine which has 32 GB of memory running on CentOS system. The programming language we used is Python. So we have used both synthetic and real world databases for conducting experiments. Okay. So PFP growth plus plus is the state of the art algorithm to find periodic frequent patterns, and CFP minor is our algorithm. Okay. Now coming to the figure 5, you can see that as the minimum support increases, okay, the number of periodic frequent patterns and the number of closed periodic frequent patterns decrease. It is because very few patterns try to satisfy the increased minimum support threshold value. You can see that at low minimum support values, there is a explosion that is happening actually. And the explosion is causing the PFP growth algorithm to terminate. Okay. On the other hand, our algorithm was generating few patterns and it was able to mine closed periodic frequent patterns even at very low minimum support threshold values. You can see the same for mushroom, congestion, and drought. As the explosion happens, PFP growth fails, whereas our algorithm still able to generate the patterns. So this is the advantage of a model. Even if you look from the memory perspective, our algorithm takes much less memory compared to PFP growth plus plus algorithm. Similarly, runtime, our algorithm outperforms the state-of-the-art PFP growth plus plus algorithm. Similarly, we have calculated the power consumed by our algorithm and the PFP growth algorithm. It can be observed that our algorithm takes very less power as compared against the PFP growth plus plus algorithm. So in this experiment, we have changed the max period value. You can see that even if we change, our algorithm generates fewer patterns, is more memory efficient, runtime efficient, and power efficient. So this is the advantage of our algorithm and the model. Now, when we look at the scalability of the figures, okay, as the database size increases, the runtime requirements and the memory requirements of both algorithms increase almost linearly. However, our algorithm takes less memory and less runtime to find closed periodic frequent pattern. So this is the advantage of our model. So now coming to the case study, previously we have seen the traffic network, right? So here these are the road segments where regular congestions were observed. So the patterns are shown here. Okay. So we can see that these are different patterns where congestion has regularly observed. When we have this information, okay, now when we interpolate the typhoon data, okay, so at 6 hours this was the typhoon, at 7 hours this is how the typhoon was, and so on. When we interpolate this data, you can see that, okay, so here we have some areas, road segments, which don't require too much attention. Attention has to be given here, similarly here. But as 7 and 8, okay, the typhoon has moved from the coast of Kobe to the innermost areas of Kobe area. So you can see that as the time is going on, passes, our attention that requires is varying. So this kind of real world information can be generated and can be used for monitoring traffic. Now coming to conclusions and future work, we have proposed a novel algorithm and a model to find periodic frequent patterns. By conducting experiments on various databases, we have shown that our algorithm is not only memory, runtime, and energy efficient, but also highly scalable as well. As a part of future work, we would like to investigate the models to find closed periodic frequent patterns in graphs, data streams, and symbolic databases. Thank you. We are now open to the questions.